Hello, everyone. Harrison with the National Renewable Energy Laboratory, and I'd like to welcome you to today's webinar hosted by the Building America program. We are excited to have Larry Brand and David Bohack here today to discuss both current guidelines and the field test study supporting revised protocols for combustion safety testing in low-rise residential buildings. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or your telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will display the telephone number and audio pin should you choose to dial in. Panelists, we ask that you please mute your audio device when you are not presenting. If you have technical difficulties with the webinar, you may contact the GoToWebinar help desk for assistance. If you would like to ask a question, please use the questions pane to type in your question. Please indicate which speaker you are addressing your question to as well. If you are having difficulty viewing the materials through the webinar portal, you may find PDF copies of the presentation at the website listed here and may follow along as our speakers present. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. We have an exciting program prepared for you today. It is often challenging for residential contractors to conduct appropriate combustion safety test procedures in existing homes and use effective actions to address any failures. Commonly used testing methods can be complicated to follow and may be overly conservative, producing false positive results without addressing the fundamental need for inspection of the venting system itself. Additionally, there are situations where comprehensive combustion safety tests are not necessary and prescriptive procedures can be used to address safety concerns. Methods to easily identify these situations and conduct the required actions may reduce test costs and provide a higher level of confidence that contractors are following the proper procedures to protect against combustion safety failures. To aid in addressing these concerns and opportunities, the Building America program is hosting this webinar that will discuss both current guidelines and field studies supporting revised protocols for combustion safety testing in low-rise residential buildings. Before our speakers begin, I will provide a short overview of the Building America program. Following the presentations, we will have a question and answer session, closing remarks, and then a brief survey. The U.S. Department of Energy's Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for 20 years. This world-class research program partners with industry to bring cutting-edge innovations and resources to market. Visit our website at buildingamerica.gov to find more information about the program and the Building America Solutions Center, which provides expert information on hundreds of high-performance construction topics, including air sealing and insulation, HVAC components, windows, indoor air quality, and much more. Building America is supported by 5 industry research teams and 4 national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and utilities. The best and the brightest in the residential buildings industry can be found here. And now, on to today's presentation. Our webinar today is Solutions for Combustion Safety in Existing Homes. If you would like more detailed information about this effort, please feel free to contact our speakers. Our first speaker today is Larry Brand. Larry is a Research and Development Manager at the Gas Technology Institute and the Partnership for Advanced Residential Retrofit, or PAR, working in the areas of building energy efficiency, project development, codes and standards, and technology deployment. He has 30 years of experience managing building systems research and product development programs for private and public companies and has launched over 20 products into the marketplace. Larry is currently the lead investigator for the PAR Building America team and principal investigator for the California Energy Commission Measured Home Performance Project. Also presenting today is David Bohack, the Director of Research with the Center of Energy and Environment. He has over 30 years of experience in energy efficiency and indoor air quality in commercial and residential buildings. He was the manager of the Center for Energy and Environment's Indoor Air Quality Group for the Minneapolis-St. Paul Residential Sound Insulation Program that performed combustion safety tests, air leakage tests, insulation and air sealing quality control inspections, and remediation of over 7,500 single-family homes and hundreds of multifamily units. His energy research includes measurements of commercial building envelope and duct sealing, aerosol envelope sealing and ventilation improvements for multifamily units, the efficiency of tankless water heaters and combustion systems in houses, and effectiveness of combustion safety protocols. His indoor air quality research includes assessments of secondhand smoke exposure in cars, apartments, outdoor patios, and bars and restaurants, the transfer of secondhand smoke in multifamily buildings, the transfer of contaminants from residential garages, and strategies to improve the transfer of airborne infectious diseases in hospitals. With that, I'd like to hand it over to Larry and welcome him to start the presentation.
Great, thanks. Let me give you a full screen view of this. There we go. So Dave and I are excited and glad to be a part of the webinar today. Before we kick off, we're going to talk about three main topics, and before we get into that, I wanted to acknowledge some of the great work that's being done by several other organizations that are working in combustion safety. So Paul Francisco for Illinois Sustainable Technology Center at the university. Dan Cotley in Seventh Wave is also a part of the work that we're talking about today, so Paul and Dan as well. Brett Singer and his team at LBNL are doing some great work in this area, and we've presented with them in the past. The CEE, Jim Fitzgerald, Center for Energy and Environment, we may hear from Jim today, as well as some of our partners with the American Gas Association, AHRI, Building Performance Institute, and ResNet. So, you know, this is a very important topic for the entire industry, and there's some pretty good minds, you know, trying to address and resolve some of the issues associated with combustion safety. So today, this is what we're going to do. I'll give you a little bit of an introduction. There were two measure guidelines developed for Building America, one that uses indoor air and one that uses outdoor air. I was encouraged not to use the term confined space, because I think that means something else now in the building inspection business. So I'll use those for now. And then we're going to talk about recent research. So Combustion Safety Simplified Test Procedure that Dave and I and others have been working on for Building America. Some survey work that was done by Paul that I mentioned, some short-term testing and monitoring, and then we'll look forward a little bit and talk about harmonization of what's in the various guidelines and codes that exist out there, and then we'll do Q&A. So I will pass it back and forth. Dave and I will pass it back and forth as we go through our own topics here. So what's combustion safety? There's a lot of discussion about you know, what is it and what isn't it, and in general it refers to natural draft appliances creating a drafted event within a short period after ignition. So it relates to excessive spillage in general, you know, in the community. This is my definition. Things tend to go back to spillage, measurement of spillage, rather than the more serious issues related to backdrafting. And then, you know, that there's a time associated with allowable spillage. So that's what we're focusing on here. It does apply to common vented, fan-assisted, and draft-hood appliances, both Category 1 appliances, you know, natural draft venting with B vents, and only in the perspective that there should be no flow of flue gases or vent gases from one appliance to the other when they're common vented. So that's a critical part of it. Good practice for combustion safety means the appliances are properly installed and are operating correctly. So there is sufficient air for combustion and dilution, and we'll get into some of that today. The vent is properly sized and installed, and I can't underline that enough. We see a lot of cases where that's not the case. And that the appliance is operating at CO levels that are within the safety certification limits. And I'll talk about that a little bit as well. I always start with the code. So the combustion air requirements and the vent sizing tables are all the same in the Model Fuel Gas Code, installation code. So here's the National Fuel Gas Code 2015 edition. There's also an International Fuel Gas Code, and then there are other model codes. And they all kind of reflect the same set of requirements for combustion air requirements and vent sizing. So I'd encourage you to take a look at those. The Fuel Gas Code here has been an ANSI standard since 1974. All the Category 1 appliances are installed according to the tables in the Fuel Gas Code. All the other categories, I believe, are have their own installation instructions. So the fuel gas code talks about category 1 only, or natural draft appliances. There was a 2015 update to NXG, if you're familiar with the code. That was, I believe, the major change since the last version, which I believe was 2012. But at any rate, the code is enforceable when it's adopted by the authority having jurisdiction. So if the AHJ references the code, then it becomes sort of the law of the land wherever that jurisdiction is. So I would start with the fuel gas code. I encourage you to take a look at it. Here's what, so getting into that a bit, here's category 1 natural gas appliances, fan assisted, drafted, equipped, negative vent pressure, not condensing. The label on the appliance will show its category. So you can look, if you're not sure if this is a category 1 or category 2 or something, look for Cat 1 on the label, and that tells you what you're working with. Water heaters with draft hoods are not categorized. I believe that's still the case. Maybe Frank Stenonik is on the line. He can he can bring us up to speed on that, but I believe that's the case. They're considered category 1 for venting and combustion safety, so they do follow the tables that you'll see in the National Fuel Gas Code. Proper installation of the equipment is important as well. So clearances to combustible materials, I want to make sure that we cover this just briefly. That's important for safety. The combustion air requirements are met, and that the appliances are tested according to the test procedures. I think today we're going to focus on 2 and 3 in that. These are the 2 Building America measure guidelines that are available through the Building America website, and you could also contact us and we can share these with you. So combustion safety for natural draft appliances using indoor air, and combustion safety through appliance zone isolation. And we'll be summarizing these 2 today. So let me go into the indoor air measure guideline, and then Dave will talk about the zone isolation. So indoor air, as I mentioned, appliance other than, this is section 9.3, air for combustion ventilation in the code, in the fuel gas code. So the air is for combustion, ventilation, and dilution in accordance with the manufacturer's instructions. So it's very important to the combustion safety and the venting process to get the air correct for the appliance. So there are some requirements for indoor combustion air using the required volume method. So there's 2 parts of this. Part 1 is if you know the air exchange rate, the air tightness of the home to be 0.4 ACH. That's based on natural, it's not an ACH 50 number. Then you can use the standard method here, and the standard method says that the volume of the space, this is indoor air for combustion, so the volume of the space has to be 50 cubic foot per 1,000 BTU per hour of the appliance. So for example, here, if you have 120,000 BTU per hour appliance, category 1, so it could be fan assisted or a natural draft, you need 50 times 120 or 6,000 cubic feet of volume that's communicating freely with the appliance. And that's about a 750 square foot area with, if you have an 8-foot tall ceiling in the home. So, if you have more than 0.4 ACH, and I think 0.4 ACH can relate to, in an ACH 50 term, I believe it's around 8 ACH 50. So that's a fairly leaky house by today's standards. So this result, part 1, is 750 square feet. Part 2, if you know that your air infiltration rate is less than 0.4 ACH natural, you can use this known air infiltration rate method in the code. Other than fan assisted, you use 21 cubic foot per ACH. If you have a fan assisted furnace, for example, you'd use 15 cubic feet. So here's my example again. Let's use 0.3 air changes per hour on a natural basis, 120,000 natural draft appliance. You would need 8,400 cubic feet or 1,000 square feet, 1,050 square feet, so a little bit more here for a natural draft. With a fan assisted, you would need 6,000 cubic feet of volume freely communicating with the appliance, or 750 square feet with a foot ceiling. So that's back to the sort of the same number we were getting in part one. So these are the two main parts of the code on air infiltration or air that's used by the appliances. Then I want to mention COs within limits. This is a table from the 2012 standard, but I believe the numbers are the same in the 2016. There's a more exhaustive list, and these are the CO air-free numbers in the appliance flue. So with a central furnace, all categories about the ANSI certification standard requires 400 ppm air-free of CO or better. So that's what these are. These are following the appliance certification standards. And you can look down the list here to wall furnaces and gravity furnaces and water heaters. And this also shows you how to do the calculation for air-free CO. So that dilution is taken out of the calculation. So make sure the CO is within the limits for the appliance. And then vent sizing is the other part of this that I wanted to mention. It applies to both zone isolation and using indoor air for combustion. And this is my opinion here on the top. Most combustion safety incidents are related to poor sizing of the vent. And you see a lot of it out there. So the venting tables in the code have been around since the 50s for natural draft appliances, and they were updated in the 80s for fan-assisted appliances, and several of us were a part of all of that. They're good. These are vent sizing tables have been time-tested, and they will address most problems. So I sort of encourage people who are having a combustion safety question or see a house that has an issue to start with looking at the venting tables in the code. So here's an example of how to use the venting table in the code. I won't go through this too much, but so you have a furnace and a water heater with various capacities. They're common vented. You go to a table like this that says this is a vent connector capacity for a type B double wall connector with 2 or more appliances. You start on the left with the vent height. You work your way across, and it shows the capacity for a natural draft appliance, which is a maximum capacity. You look up your appliance, or the fan-assisted furnace in this case, you look for that range. And then this tells you that you have a 4-inch a 4-inch double wall connector for the water heater and a 5-inch double wall connector for the furnace for this particular case. It's fairly simple, but I encourage people to take a look at these connector sizing tables and some of the other information available on laterals that's in the code. When you get a situation and you're not sure why it isn't working correctly. I have some pictures later on that I'll show you some installations that maybe aren't according to the code. But so that's my set on indoor air for combustion, and Dave is going to talk about the zone isolation option. Dave?
Okay, thanks, Larry. My understanding is that reason this came about is that there was an expert meeting for Building America, quite a bit of discussion about the concerns with the ability of contractors to properly do the combustion safety testing under worst case conditions and be able to set up worst case. So tried to identify situations that would be straightforward for contractors and that something that they could implement maybe without the uncertainties of testing. And so the one situation that was identified was where the furnace, water heater were in an isolated zone all by themselves away from the house. And so this measure guideline focuses on that. And just want to mention too, as Larry noted, Jim Fitzgerald, who was the co-author on this, is with me here today. And for those of you who know Jim, know that it's very likely he'll be chiming in along the way. So Larry, if you want to go ahead on to the next slide. So again, these are natural draft appliances located in enclosed space, typical locations, mechanical closets, off of the living space, attached garages, attics. And what we're looking at doing is, providing a proper air barrier to make sure that those appliances are truly isolated from house and really house depressurization, and also providing combustion air from the outside to make sure that they have sufficient air. With the expectation is that this would then eliminate the need for doing any depressurization combustion spillage testing. So if you can make sure that these kind of prescriptive measures are complied with, then you don't have to worry about depressurization in the house. Go ahead, Larry. So the 5 steps that are involved with this. Number 1, Larry finished off his discussion with talks about combustion venting system. Make sure that the combustion venting system is sized properly according to codes. I'll just echo that. We tested thousands of houses with our sound insulation program, and what we found was of the houses that were spilling under worst case conditions, that even if you took away worst case conditions entirely, still half of those were failing in spillage or under what we called natural conditions. And that if we just had those venting systems modified so that they met code, that spillage went away. So number 1, make sure that the combustion venting system complies with code. Number 2, make sure that you have a good air seal for that physical boundary. You need to make sure everything is sealed well. Number 3, ducts and cabinets, air handler cabinets are in that isolated zone. You want to make sure that they're sealed. Any leakage to the return duct and the return side of the blower is going to pull in air from that space, depressurizing the space. And then also if there's any spillage, any combustion spillage is then going to get pulled into that air handler and distributed to the house. So need to make sure that ducts and cabinets are sealed properly. And then make sure that we have number 4, properly sized combustion air openings. And then number 5, although it's not really recommended, that you really don't want to have exhaust appliances in that space. If they do, make sure that you have adequate makeup air to deal with those. Why don't you go ahead, Larry? If you move on to the next one.
Hang on a second, I seem to be stuck here. Yep, I am. There we go. Is that the next one?
Yep. So Larry already covered the issue about looking up or using the code tables for combustion venting, so I won't talk any more about that. Sealing the enclosure, you really need to make sure things are airtight. First of all, if there's any large openings, use sheetrock to seal those up. And then any other small gaps, seams, penetrations between the living space and the zone, kind of use your normal sealants, joint tape, sealant foam, make sure it's listed for use as a fire stop and approved for uncovered use, or sealant caulk. And then very often, especially mechanical closets will have a door to the house. You want to make sure that that's weather stripped, has a nice quality seal on it, and really you'd like to have that be self-closing and latching so that there's not an opportunity for people to be able to leave that closet door open. Sometimes we've seen those doors with louvered doors, and certainly that's not something that you want to do to try to isolate that space. So you either replace that or make sure that you block off all the louvers. Go ahead, Larry. Number 3, the duct and cabinet sealing. Again, you need to seal all the gaps and so forth. Straightforward thing is you want to make sure that you have a continuous sealed duct from the living space to the blower housing. In general, what you'd like to see is that duct area is the same as the area of the return inlet, or at least 2 square inches per 1,000 BTU of output. And that's recommendations that were come up with from Proctor, Chitwood, and Wilcox in their work. And then finally, you also need to have that mechanically fastened the duct to the blower housing. You want to tape all the cabinet service openings and joints of that air handler for the furnace. and that you're going to be doing with that with mastic and mesh tape, with the UL 181M compliance, or foil tapes with UL 181AP or BFX compliance. And then, of course, you don't want any return air from that space that's going to depressurize that or cause you to bring air in from that space and distribute it to the house. Go ahead, Larry. So as far as combustion air from the outside, again, follow the code. It works. If you have two openings, you want those the one at the top to be within 12 inches of the top and the one on the bottom 12 inches from the bottom. The diagram on the left shows when you have either direct or vertical ducts out to the outside from the space. In that case, you need an opening of 1 square inches per 4,000 BTU hour input for the appliances that are in the space. If you have those going horizontal, then you need more, so you need 1 square inch per 2,000 BTU per hour input. Go ahead, Larry. And the other option there, you can go ahead and get by with one opening. That should be within 12 inches of the top, and now you need a square inch per 3,000 BTU per hour input. But it also needs to be not less than the sum of the area of all the vent connectors. And when you're looking at this, you need to make sure that you consider the effect of any louvers, screens, or grills. Use the manufacturer guidelines for how to derate that opening. If there isn't any label, then the guidance is you assume 75% for metal louvers and 25% for wood louvers. Go ahead, Larry. So makeup air and exhaust fans, again, the best thing to do is just make sure you don't have any exhaust fans or dryers in that space. If you do have a dryer, the code recommendation is for 100 square inches of opening. It is allowable to have a damper on that opening, but it must be interlocked with the dryer. If you've got a situation where that equipment is up in the attic, you need to make sure that you either remove or disconnect any powered attic fans so that they're not going to be causing depressurization, or you need to follow the manufacturer recommendations for the amount of air inlet openings that you would need to properly compensate for the amount of air that would be needed for that fan. Go ahead, Larry. So that's kind of the way of coming up with your work scope for an isolated space. You get that work completed, and these are the measures that you would need to do to confirm that everything has been done appropriately. So first, just a visual inspection of kind of, again, those gaps and leaks in the air handler and ductwork. Make sure that those have been properly sealed. As a follow-on to that, to really ensure that that's been done properly, you'd like to smoke test the duct and cabinet leakage. And that involves taking a fan and pressurizing that cabinet and ductwork that are in that isolated space up to 25 pascals. Bring theatrical fog into the system, and then look at that ductwork and cabinets and see if you have any fogs that are exiting any of those spaces. If you see anything leaving there, you need to seal it up. And then finally, you want to make sure that your air sealing of that enclosure has been done properly. So our recommendation is that when you have the house pressurized to 50 pascals, you'd like to see that isolated space be depressurized by no more than 5 pascals, so 1/10 of what you get in the house. So it's not 100% isolation, but we feel this is a good guideline or a good rule of thumb that'll provide adequate isolation in almost all cases. You also want to take a look at the HVAC operation and make sure that it doesn't depressurize that space by more than 1 pascal when it operates. If you do have a dryer in the space, you want to make sure that that doesn't depressurize the space by more than 2.5 pascals. And same thing, if you're in a garage and there's an exhaust fan in the garage for ventilation, you want to make sure that that doesn't depressurize by more than 2.5 pascals. Go ahead, Larry. So I just want to note, in the measure guideline, there's case studies provides a little bit more specific guidance on a few situations. One is the attic furnace, 2 is the attached garage, and 3 is a mechanical closet with particular attention to when you have a door to the bedroom or a bathroom, and when you have a building cavity that's being used as a return. So you can look at the measure guideline for more information on those situations. Go ahead, Larry. And I just wanted to point out, too, that one of the key details that is often overlooked or is difficult to deal with is that return platforms underneath the air handler, and there is a nice guidance on how to do that air sealing that was provided by Ray David from NREL. Go ahead, Larry. So just to sum up, this is meant to be a very straightforward kind of prescriptive measures to isolate that space. Use inspections and that isolation test to confirm that you got the appropriate amount of isolation. That's going to protect the natural draft appliances from house depressurization, so now you don't care how tight the house gets or how much exhaust you have in the house. That's going to be isolated from your combustion appliances, and then it eliminates the need for depressurization combustion spillage testing. So back to you, Larry.
Great. Thanks, Dave. We also wanted to cover some of the more recent Building America research that we've been doing over the past actually year or two, in addition to the measure guidelines. So we have a section on that here. We're looking at field test procedures here, and the question is setting up the worst case depressurization that you could create really necessary to catch combustion safety failures. Is there a way to do a more simple test procedure and still catch the cases that you want to make the safety cases and get fewer false positives, so you're not you don't start out an upgrade for a home by replacing appliances that may or may not need to be replaced. So in the past couple of years, there was some activity sponsored by Building America to do some research on field performance and the opportunity for doing a simplified combustion safety test procedure. So here's the scope. We started with a survey, working with weatherization teams around the country to get their experience on how they approach this issue in the field. What kind of testing do they do? Do they have guidelines that they work with? And there was quite a bit of great information that came out of that. And then there was a field evaluation looking, starting with a simplified test procedure. With that, the major components are fixed door positions, air handler if it reduces indoor air pressure, and clothes dryer on. I have a little more on simplified test procedure later on. And then sites were selected based on for the field testing where there was significant data collection. The house had to fail a must-fail criteria and it had to pass a must-pass criteria. So we needed to identify houses that were in this range that could potentially have a combustion safety failure. So the must-fail had the kitchen fan operating on high, the next largest fan on, and looked for continuous spillage after a set time, and the time depended on if it was heating season or not heating season. And then there was a must-pass criteria where the kitchen fan could be either on high or low, so we made it a little bit less severe. The next largest fan could be on or off, and then also required no spillage after a set time, and that's a time range that we'll talk about. So that's the overall scope of the whole program. Here's the simplified test procedure that we identified. Paul, Francisco, and I, and Dave, and Pat, and lots of folks were working on this together. So this is how you set up the house. Keep the doors open if there's a return or exhaust in the room. Otherwise, you would close the doors. that's as opposed to the way BPI used to do it, looking for the worst case door position. A little simpler for the field tech. Turn on all the exhausts, including the dryer. And I have a star under exhausts because I think in some cases you have to identify the speed of the fan for the exhaust. And then check for if the house is more negative with or without an air handler operating. And if you take the most negative case, and then you check with and without the combustion appliance zone door open, and you take the most negative case there as well. And here are the spillage limits. So beyond 2 minutes for water heaters and furnaces in heating mode, if that was a failure, if it spilled past that amount of time, and 5 minutes for furnaces not in heating mode. The assumption here is that in heating mode, those appliances wouldn't be cold, so you'd be likely working with a warm water tank at least, or a warm heat exchanger in the furnace. And then, of course, as I mentioned before, checking the CO against the ANSI certification standards. So these were the three major elements of the simplified test procedure that we were trying to collect data around. And I'll take you through the survey, and then Dave will talk about the field data collection. So on the survey, the work was done by the Illinois Sustainable Technology Center. So we were trying to identify how common the combustion safety failures are out there in the field. There's a lot of anecdotal information on, I think there was a study in Canada done many years ago that said about 10% of the homes had failures for combustion safety reasons and needed remediation. I think it was back in the 80s. So we're trying to figure out how, what does that really look like with real data. National Association of State Community Services Programs were our partner on this, and they disseminated the survey vehicle. And you can see here which states were surveyed. Not all of them provided responses to the survey information, but we did get quite a few, and you can see. So there were two parts to the survey, and I don't have a comprehensive list here, but we did ask questions about the housing and that they had worked on in the last program year, how many homes were treated, how many homes used fossil fuels, and then how many had natural draft appliances within the pressure boundary to identify where depressurization could cause a concern. Outside of the pressure boundary, if you follow the zone isolation rules, then it should be immune to depressurization-related combustion safety failures. We asked them what test procedure they're using. Is it BPI or some other procedure? And we're looking for granularity on the houses that failed. The test procedure they were using, do they know how many were due to air handler operation or exhaust-related, including dryers? How many had in how many cases was the appliance taken out and replaced with a new appliance? Or what was the use of power vent kits for remediation? And then how many houses had deferred weatherization because of the issue? So here's the home sample size, 30,000 plus houses. 94% of those were WAP, weatherization assistance, low income homes. Well, there's a low income requirement for WAP. So a good, population of those. 78% were oil, gas, and propane, so many were using fuels like that. One state said they didn't track they had some data, but they didn't track the program with the granularity we're looking for. So in the end, I think we had 28,000 plus WAP homes, 30,000 homes in the program. So pretty good sample. So 6 states provided estimates. I'm getting an echo. Sorry. They report 41% of the houses had natural draft appliances within the pressure boundary, so that's pretty good. There were 4 states that had precise values, had better record keeping, and they said that 81% of those homes had natural draft appliances within the pressure boundary. And then 7 states didn't track it at all. So the difference, we believe, between the 6 that provided estimates and the 4 that had precise values was related to geography more than it was to whether or not they were keeping good track of their data. Anyway, so a pretty good proportion of the homes had appliances within the pressure boundary. So the states that did have good data, so this is survey results on failure rates. The states that did have good data, there were 4 of them, and 4% of the houses were remediated because they had some expected failure in the home, and about 5% were remediated because they did do the test and observe the spillage beyond the spillage limits. In the states that didn't have precise data but had estimates, about 6% were remediated because of expected failures, and 16% were remediated due to observed spillage. But that included Alaska, which estimated about 40 to 50% of their homes were remediated because of that. That's a little bit of a tough data point. So if we take that out, we had about 8%. So if you had good data, you were in the 4 to 5% range, and the states that were estimating give us from maybe the 6 to 8% range of remediation. So compared to the Canada study from the 80s, it looks like there are fewer cases where remediation happens than we would have expected. The pie chart just shows the number of houses for the states that had data, that had estimates, and had no data. I left the no data case out of here, so a lot of states didn't track. Also, so failure causes. So we asked to go a little deeper. So the states that did have good data said 4% of the homes failed because of the air handler operation, which is a little bit of a surprise to us. And then 4% of the homes failed because of exhausts, and that exhaust could include dryers. So we're in the we can identify what percentage is associated with these different things. So that's a very high number for air handler operation, and it tends to take us down a different direction. And then the performance of the dryers, I know the industry has been talking about the contribution of dryers to depressurization, and this would tend to support that. On the states with estimates, 6.5 failed because of air handler operation, and about 18% were on the exhausts, including dryers. So quite a bit higher, where good data it wasn't tracked quite as well. I guess you can make your own decisions about that. Also, compared to states providing precise data, this is in general, states providing estimates said that homes failed spillage tests at a higher rate, and that exhausts are more frequently the cause. So this kind of gets back to the more of the anecdotal information that we have in the past. It tends to overestimate what the failures are, the failure rate, and it tends to point to exhaust more frequently when maybe we saw some data here that showed that it could be distribution systems issues, their duct systems. Could be correct, but because of the small sample and geographic differences, tough to say. Some states volunteered that most failures are due to, or many failures, in addition, I think, to those major items, are improper flue sizing, roof caps that are crushed for one reason or another, and then the air handler operation, the dryer operation. So pretty interesting stuff. So remediation, states with data, 31 or 3.2% of the homes got new appliances. And the states that had estimates, if you take out Alaska, 2.3% received new appliances. And Alaska estimated about 60%, so they're running their program a little differently. So those are pretty comparable. So we're into the 2 to 3% neighborhood. The power vent kits, which we thought would be a really good solution in most cases, aren't that commonly used out there. Only less than 0.2%. Not sure why that's not used as frequently. It's a less expensive option. And 6 homes in one agency deferred the upgrade of the insulation, the weatherization. So it's very infrequent that the weatherization doesn't happen due to a combustion safety related issue, which I think was a question that we had at one point. So conclusions, failure is not as common as expected, maybe half of what was expected, it's in the 3 to 5% range. Not often due to exhaust fans. We did find a lot of air handler or dryer or vent failures that could be more likely the root cause. Air handlers, so to speak, because of the leaky duct systems. And then very little actual tracking of the information. So we see a research opportunity here for the future, getting better granularity and actual, working with weatherization agencies to get good data on failure modes. Okay, and that's the survey part, and I'm going to turn it back to Dave to talk about the field study. Dave?
Okay, thanks, Larry. So in addition to this survey, there was also a field component to the study, and that is we wanted to take a look at houses that failed the simplified protocol for spillage and yet passed when they were put under less extreme depressurization conditions, to look to see how often those appliances actually spilled. So the question is that, is the simplified procedure properly identifying appliances that are prone to spillage? Is it kind of overestimating the amount of spillage that might occur, or underestimating? We used 11 homes, 10 of them in Minnesota and 1 in Wisconsin. We were looking for homes in other parts of the country and had reached out to other organizations to help identify those homes, but it turned out it was quite difficult to find houses that had this kind of narrow window of opportunity, that that it failed under simplified depressurization conditions, and yet when you turn the kitchen fan to low and other exhaust fans off, then it just passed. So there's a smaller number of houses where that occurred. So instead of seeing a national study, this was centered on Minnesota and Wisconsin. So for all of those houses, we did a series of short-term tests, and then we also went in and put monitoring equipment in, looked at the burner operation, so when and how often the burner is operating. We used CO2 monitored near the draft hood as an indicator of spillage. I should say that Dan Cautley from 7th Wave put together all this monitoring equipment and was responsible for compiling the data and doing all of that analysis. And so what he was able to see is that if you monitored CO2 near the draft hood, that when there was spillage, you'd see a sharp rise in CO2 concentration, and when there wasn't, it might be more gradual, or there'd be none at all. So that seemed to be a very reliable indicator of spillage and the duration of spillage. In addition, we were measuring the pressure in the combustion air zone, or around the appliances, relative to outside, and we were looking at the status of all the exhaust fans. So the status of the dryer, when is it running, kitchen fan, bath fans, and also for some of the houses we were able to take a look at whether the door closest to the appliances was open or closed. So we collected that data from anywhere from 3 to a little bit over 6 months, and we ended up between those 11 sites of having about 1,500 days worth of data. This monitoring started in February and then ended in the summertime. Go ahead, Larry. So these plots give you an indication of the amount of spillage, or number of spillage events by minute of operation and by site. So, MN01 is the first house, and all the way through MN10, and then WI01 is the house in Wisconsin. The bars that are kind of maroon or red indicate that those are the events where there was spillage, and the ones in gray indicate that those are, well, all of the events for that water heater. And from left on the 0 means that, let's see, this data was binned by number of minutes into the operation of that burner. So on the left means that there was 1 minute of operation, and over towards the right 15 minutes. So typically 2 to 5 burner events per day for these houses, and 5 minutes or more was the typical duration of the burner cycle. So you can see right off that MN04 and WI01 had significant amounts of spillage. So it turns out of all of the operation of that burner for those two sites, for MN04, 47% of the time there was spillage, and for WI01, 91% of the time there was spillage. But otherwise, if you look at the rest and you look at all of the operation, the fraction of time that there was spillage varied from a low of 0.3% for one of the houses up to 5%. And of the other 9 houses that didn't have significant spillage, MN01 had some significant spillage, but really only in the first minute of operation, and pretty much the same is true for MN03. And if you take out those 2 houses, what you would find is that of all the rest of the houses, there was spillage for 1% or less of all of the burner operation for those water heaters. And I should reiterate here too, these are water heaters that when tested under a simplified protocol for depressurization, that they failed that combustion spillage test, or that there was spillage beyond 2 minutes of operation. So this is kind of real world operation of a water heater compared to what you'd get from a short-term test. So in all of these cases, a regular depressurization test would say that it's failed and that they'd need to be replaced. And yet in certainly 9 of the 11, when you look at the frequency of spillage, it's around 1% or less if you ignore the first minute of spillage operation. And kind of going back to what's causing this, MN04 and WI01, these are vent system problems. Larry, if you want to go ahead and move on to the next slide. So both of them had vent defects. MN04, they have a picture there on the right. So it has a 3-inch vent connector off the water heater with a 6-foot run and 4 elbows. And when you look in the National Fuel Gas Code sizing tables, then the vent capacity was actually 75% of the burner input, and you would like to see that to be 100% or greater. W01, there was actually, that was previously common vented with a furnace, and the furnace was removed, but the vent had stayed in place and was still partially opened on the end of that vent. So in both of the cases where we saw significant spillage, it turned out that it was a vent system issue. If you want to go ahead and move forward. So this is, Dan and the people at Seventh Wave did a logistic regression model to look at the factors that contributed to spillage. And, what they were finding in there is that, again, the model says that 04 and 01 were the only ones that had significant amount of spillage beyond the first minute. That's those red bars. In 01 and 03, there was significant spillage, but only for those first minutes. That's the blue bars. And they also looked at the effect of outside temperature, and you can see in these cases that there is a increasing incident of spillage with warmer outside temperatures. And we've seen the same kind of thing with our sound insulation program and testing, that water heaters, when we did a short-term test, we saw higher failure rates in warm weather conditions than in cold conditions. Should I go ahead and move on, Larry? So we are also doing short-term testing there, and we were measuring the depressurization of the combustion air zone relative to the outside. And we were looking at what that depressurization level was for our simplified protocol compared to, in this case, it's a very comprehensive test. So if you use pressure to indicate whether the interior doors should be opened and closed, and that includes bedroom doors, doors between floors in the combustion air zone, and then if you also use pressure to indicate whether your air handler should be on or off, and you turn on all of the fans. These are the 11 houses, and how the simplified depressurization on the x-axis, how that compares to the comprehensive test depressurization on the y-axis. So for the most part, there's not very much difference between the simplified depressurization and the comprehensive, except for in one case, and that turned out to be MN 06. And in our simplified protocol, we weren't turning on, so we turned on the kitchen fan to high, and the next largest exhaust fan. If there was a second bath fan, that was not turned on for the simplified protocol. And it turned out in MN 06, there was a 68 CFM exhaust fan in the second bathroom. And in addition, in our simplified protocol, we were always closing the door closest to the CAS. And in this case, it turned out that depressurization was worse with that door open. And then also there were 2 main floor bedroom doors where using pressure as an indicator had those be closed instead of opened. So that's the reason for that 1 point, the difference between the simplified and the comprehensive depressurization measurements. Go ahead, Larry. So we also looked at using the BPI protocol for setting up the house in depressurization conditions and how that compared to the comprehensive. And so now you're looking at mainly the difference between using pressure to indicate whether interior doors should be opened or closed or not. And so you can see for at least our 10 or 11 houses, very little difference in using pressure as an indicator or just whether there was an exhaust fan or return in that room. Go ahead, Larry. So, some conclusions. Again, this was turned out to be a 100-page final report that included information on the survey and the short-term tests, all of the monitoring data, an awful lot of information that came out of this study. I'm hitting really just the high points. Overall, though, what we were finding is that normal systems that had properly sized venting systems weren't spilling excessively, and they weren't producing much carbon monoxide. And these, again, were ones that failed a depressurization spillage test. Again, the vent defects were an important cause of the problem. And the worst case conditions were about equal for the simplified and comprehensive methods, except for the one house out of our 11. Now, I should also note, too, we were doing another test, a cold vent establishment pressure test, looking at what's the level of depressurization that this water heater can vent against, or when you back off on the depressurization, at what level of depressurization will the water heater stop spilling and vent properly. And for the ones in our study, we saw a great variation, anywhere from minus 1.7 up to minus 1.6. And that would be probably similar to a standard that you would use as a level of depressurization, that when you go above that, you would expect to see significant spillage problems. So most people might use minus 5 as that guideline, what we're seeing is that a number of the water heaters were less than a -5, but then some of them were actually above that -5. And I think, Larry, that wraps things up for the field part.
Great. Thanks, Dave. As Dave mentioned, there's 100 pages of really good stuff in there. So I'll give you the report information in a second. There's some really good work, and there's some good data to be analyzed and evaluated some more, I think. Harmonization, I wanted to just make a comment about harmonization. Part of the work that we were doing was to take a look at all the differences amongst the various codes and practices. And the top part of this box above the band in the middle is the older codes, 2012, 2011, the fuel gas code, ACA, and BPI and NREL standard work specifications. And the bottom part is updated versions of those codes or recommendations. And you can see where in the top there's quite a variety of whether, does the CAS door open or close, or do you evaluate? What about other doors? Was the air handler considered? What's the spillage limit? So there's quite a variety. And at the bottom, you're seeing more commonality, I think, between the recommendations from the various organizations. We were a part of the BPI procedure, redevelopment of the BPI procedure, so that actually is a tech transfer vehicle for much of the simplified combustion safety work that we did in this project. Tips, just a couple of things I wanted to put in here at the end. Check the vent connector. I think we've got the message across. Too long, too narrow, corroded. Consider type B. Here's a picture, a photograph from one of the reports, and it's hard to tell where that connector is going. So another option, if you look at the tables, and the tables will allow a larger diameter vent connector to get more within the appliance capacity, then that sometimes has a beneficial impact. Chimney liner when downsizing appliances. I know that's all in the code now, but if you're taking out an appliance or significantly reducing the capacity, then the chimneys need to be considered and you need to be relined. Unblock the combustion air openings. One of my favorite pictures is someone who left a warning and then it's totally blocked. So unblock those, look for them and unblock them. Use the latest test procedures that are available. Look for 2015 versions, and then consider a power vent kit, which I think is a pretty good solution. Here's the reports that we discussed today. I think these slides will be available, so you can go to the NREL and the DOE websites and pick up these reports. The simplified test protocol field study is what we've been talking about for the last 15-20 minutes or so. And that's it. So I think at this point I'm turning it back, and we are more than willing to answer questions.
Great, thank you so much. We have a number of questions. I'm just going to start with the ones that came in at the beginning of the presentation, and then we'll work through. So Larry, from your part of the presentation at the beginning, we had the question whether you had any idea what the impact has been regarding combustion issues in energy efficient homes being built.
In new construction, is definitely tighter because of a variety of things. State building codes are the regulations. It will also tend to have fan-assisted furnaces instead of traditional, and but there will be atmospheric water heaters in many cases. So in some cases, we're seeing that work quite well in new construction. In some markets, they use zone isolation exclusively, so that's a good solution. And then in some cases, the builders prefer to use fan-assisted appliances altogether to avoid any kind of issue with combustion safety. So it can be very much a mixed bag.
Okay, great, thank you. We had a question from someone who said it was their understanding that power vented appliances and high efficiency furnaces do not require fresh air inlets, but do they?
If the Well, if it's a direct vent appliance, then it will come with piping to provide its own combustion air. So those would generally be Category 4 appliances. There are some Category 1 appliances. Rheem had a furnace that I'm aware of that did have a pipe and use outdoor air for combustion. So it can, if you're in Category 4, not as much of an issue. Air is supplied. If you're in Category 1, then you still have to look into this.
Okay, great, thank you. And there was also a question about which states provided that precise, valuable data to the survey, and I'm not sure if you can reveal that or not, but someone was curious.
I don't have that here, but if you send me an email, then I will forward your question along to the people who have all the data.
Okay, great. Did the field data include measurement of carbon monoxide levels in the quote-unquote failed homes?
Dave, you know?
I know when we did the short-term tests that it did. I'm looking pretty quickly right now. No, it was just CO2 measurements, but we did put a carbon monoxide detector in the space itself. But nothing in the flue.
Okay, great. And then we had another question about whether it was carbon dioxide or monoxide being measured in the draft hood. So I'm assuming from your answer that would be dioxide.
Correct.
Okay, great. All right. And then from the part with the graphs, we had someone say that it seems like the graphs are saying that even when there is spillage, it rarely lasted longer than 15 minutes across all the measurements. Is that correct?
Yeah, the graphs go out to 15 minutes. I'd have to check with Dan, but I believe that was because there weren't that many cycles that lasted beyond 15 minutes. But if you want to go on to the next one, next question, I'll take a look at that real quickly and see if I can provide an answer.
Yeah, sure. Do carbon dioxide measurements also include effects from fuel-fired ovens and ranges?
Well, in this case, I don't have a diagram, but there is a nice diagram in the report that shows the location of the CO2 sensor. Actually, these were pumped sensors. So the inlet for that was placed right at the edge of the draft hood. So we were, would have been far away from any other combustion appliances.
Okay, great. Someone was wondering if we could just repeat what the differences are between a simplified and a comprehensive testing approach and give us an idea of how much time was saved by employing the simplified test approach.
Well, I think at a high level, in the past, it was the I don't know if it was comprehensive, but it was worst case depressurization testing. So the tech would cycle through the house and open and close doors till they identified the door position that provided the worst case depressurization for the gas appliances or the appliances. And then exhaust fans, I believe, were all operating. So that was the general approach in the past: identify the worst case and then evaluate based on that. The more simplified approach, that I summarized in here was, you pick a door position depending on if there was a return air or a jump duct, I guess, in the space itself. So you took a look at the room and then identified the door position requirement. And then we did evaluate a couple of options for exhaust appliances. So the ventilation system was operating, the range hood was operating, and then the dryer was operating. So there, so it's slightly different than all of the exhaust fans operating at the same time at maximum speed. There's quite a bit of that detail in the report.
Okay,
So,
great, thank you.
One thing I'll add to that too is it's maybe, I mean, part of it might be a little bit of a time savings, but it's just more straightforward to describe to a contractor how to do the simplified test. If you're only looking at whether there's a exhaust fan or a return, that's a little bit simpler than having to do a pressure measurement under a door or use smoke under all the doors and figure out, is it positive pressure or negative pressure? And, for people that do one or two of these every day, it becomes very straightforward and routine. But for a contractor that might only do it once a week or once every couple of weeks, it becomes more confusing.
Okay, great, thank you. Do you have any advice, data, or anecdotes about CIS testing in multifamily buildings? And are there any other tests that need to be considered for multifamily testing?
Could you give me the first part of that question again? I didn't catch it.
Yeah, it was just advice, data, or anecdotes about testing in multifamily buildings.
Multifamily. Wow, there's a good research topic for you.
We have some experience with by the airport with 6 or 8 buildings, and we went through opening all the doors to all the units and finding all the fans and all of everything else in one building, 12 units, maybe more, and found that in that building and what looked like in all the other ones, the only door that mattered was the mechanical room door. And we found most of those wedged open and dryers present in all the mechanical rooms. So we didn't have to do any of the complicated testing normally done in houses and concentrated just on the building mechanical room.
So we'll say that's a situation where there's a central boiler,
right,
and not individual units in each unit. That's what Jim was describing.
Central water heater, central boiler, with laundry in the same room. Stupid design, but that's what we saw. And that's all we had to test.
Great, thank you. So we had a couple questions about whether this study informs BPI to simplify their comprehensive test, or if they've chosen to focus on a worst-case scenario to be conservative. Can you speak a little bit to whether the testing represents a worst-case scenario, or whether it should be modified?
Actually, that's a good question. Paul Francisco and I and Dave and Pat have all been working on the BPI committee that's revising their test procedure, and actually we've got quite a bit of the simplified method in that test procedure now. It's not identical, but it's a major step in the right direction. So if you pick up the newest BPI test procedures, you're using a lot of the simplified method developed here.
Okay, great. Dave, can you mute yourself while you're not talking? I think we're getting some feedback. All right, thank you. All right, someone asked what you recommend for wood stoves and fireplaces, since these can't be isolated.
I myself haven't studied wood stoves and fireplaces and their effect on combustion safety. I think the recommendation is that you just close the damper to a fireplace. I don't know, Dave or Pat, have you done anything there?
Well, our recommendation was always that, wood fireplaces aren't, well, you need to open up a window to make sure that they start drafting properly, and that in tight houses, you very often will have problems with wood fireplaces and wood stoves. And what often is a problem is that maybe you might get a good draft at the very start when you have a roaring fire, but it's the time where that's kind of dwindles down, that you don't have such a hot flue anymore, and that's also a time where you can be producing higher levels of CO. That was our recommendation to people.
Have to have a CO alarm in the space. And I was tasked with following up on the complaints of wood smell, and we found in houses with basements, 2-story chimneys, that airflow in standby condition was from the fireplace into the house. Cold air would fall from the fireplace into the house all the time, even in the summer with all the windows open. It's nuts. This is with old masonry fireplaces in the house. Now, if somebody's using wood for heat, then the advice we gave was to use an EPA-listed insert or direct vent gas logs, if they're doing. But following up with existing fireplaces, the mechanical inspector that taught me the most said, "Why are you looking at that junk?" They're very difficult to make into more than a hobby. So people want them, and they're an important part of real estate transactions. So I don't know if that's helpful.
So one thing I want to point out too, while I'm thinking of it, is that my email address, I missed this, is misspelled, so it just should be first initial, last name, dbohac@mincy.org. But sorry for not catching that.
Oh, thank you for bringing it up. We actually had someone ask already.
I don't know if it's not going to let me change it. There we go. Is that right, Dave?
Yep.
Okay.
Great, thank you very much. Just a couple more questions. Someone asked, what if there's a supply in a bathroom that overpowers the exhaust fan? Would you still leave the door open?
I think by the simplified protocol, yes.
Yes. Yeah.
If you were going and using pressure as a determination, then possibly not. So that would be kind of one of those nuances that you potentially could catch by looking at pressure across a door that you wouldn't with the simplified protocol. So there's a trade-off there.
Okay, great. Thank you. And then someone said the presentation mentioned power vent kits a lot, and that they looked into this recently and found that the code says that the appliance must be listed and labeled for such use. Natural draft appliances do not appear to meet this requirement, making aftermarket power vent kits not allowable by code. Is this consistent with your understanding?
The power vent kits are available, and you have to, it's not a modification of the appliance, so you have to look at the manufacturer's installation instructions for the power vent kit. That's my understanding of how they work. Have you used them at all, Dave?
We used them for a period of time in our sound insulation program, and had an interesting interpretation from our code officials that when we were putting them on water heaters with a standing pilot, they were uncomfortable that if you were side venting those, that the pilot could potentially be spilling into the space, and because you were blocking the vent with the motor, and for that reason they wouldn't let us use them, which seems kind of counterintuitive, because how many how many stoves do you have out there with the standing pilot and ranges? And that's fine, but a water heater isn't. So
we did have repeated complaints and calls to the fire department of gas odors in the house from pilot spillage on a boiler. After the boiler gas valve was updated to a modern one with an electronic ignition, there was no issue. But we ended up having to we had to pull out 24 draft-inducing fans and kits that either homeowners had installed or we had installed as remediation. Okay. So that's more than all of the kits reported in the 1,700 or the 28,000 in this survey.
So it looks like that's a good point. You have to check the listing to see if there's any kind of violation, listing of the code.
It's really hard to tell somebody that's just the right amount of gas odor in your house. We can't ever go there. And if you think that's funny.
Oh boy.
All right, great. Well, thank you very much to our presenters. I think we're going to move on to our short survey, and then we're going to wrap up the webinar. If we weren't able to get to your question, we will try to follow up with you offline. So thank you for all the questions that were submitted. So we'd like to ask everyone in the audience to answer 3 questions. The first question asks whether the webinar content was useful and informative. Please take a moment to choose your answer. The second question asks about the effectiveness of the presenters. All right, and the third question will ask whether the webinar met your expectations. Thank you for answering our survey. Your feedback is very important to us. You can subscribe to receive notices about upcoming webinars and other news at the URL that's currently on the screen. On behalf of the Building America program, I'd like to thank our expert speakers for their time today, and to our attendees for participating in today's webinar. We've had a terrific audience, and we very much appreciate your time. Please visit the Building America website to download a copy of the slides and learn more about the program. We also invite you to inform your colleagues about Building America resources and services. Have a great rest of your day, and we hope to see you again at future Building America events. This concludes our webinar.